We're going to dedicate this whole class session to reviewing for exam number 3 on chapter 8 in your textbook. And the topic is chemical composition. We've introduced a number of topics during the lecture last time we met, but this session is going to take those the next step, solving problems. So what I've done was I took the review document that you have available in Brightspace and picked out, highlighted some of the problems, some of the questions that are unique and I think would be useful to review for the exam. So that's where we're headed. All right, we're going to look at number 1. The number of grams in 2.58 moles of sodium carbonate. So we're given 2.58 moles of sodium carbonate. First question you ask yourself is, well, what is the question? The number of moles of this compound. If we know that we have the number of grams of that compound if we have this many moles. So when you see those two terms together, grams and moles, one of them is a question, how many moles or how many grams? That's usually a one-step process. Except in this case, you can't do what you need to do with the English name of the compound. You have to know the formula. That's why early on in the semester, I insisted that you both learn the symbols and then learn how to write the compounds. Nomenclature. All right, so sodium carbonate is what type of compound? If this is the name, it's either a type 1, type 2, or type 3. Well, look at the metal, sodium. Where do you find it? It's in the first column, alkaline metals. It's always +1 charge. That means that this is a type 1 compound. And that also means we don't have to say what the charge is because the charge is always +1. So what about the rest of the name? Carbonate. Is there any element in the periodic table that's carbonate? There's a carbon, but there's no carbonate. That is a polyatomic ion. So you need your table with the polyatomic ions and look it up. Carbonate is CO3 with a 2- charge. So with type 1 and type 2 compounds, you balance the charges so that the entire compound is neutral. Balance the positives with the negatives. You have 2 minuses here, you have 1 plus there. That means you need 2 of these to balance that 2 minus. So there's your compound. Now what do we need to do to determine? Well, if we're starting off with this many moles, right, and we want to end up with so many grams there, you need a conversion factor that will cancel moles, right? Denominator, numerator, numerator, numerator. So that says you need the molar mass of that compound. And the molar mass of sodium carbonate, go to your periodic table. Right? Sodium is 23, so we need 2 of them. Let me put that up on the board. So sodium is 2 times 23. There's 1 carbon, 12.01, and there are 3 oxygens. Right. So if we do that math, I think that's right. Yeah. If we do that math, we have 46 for that one, then add 12.01 for the carbon, then add 3/16, which is 48. It's 106.01, 106.01 grams per mole. Right? So thinking's done. From here on in, it's number crunching. So you just take that value times 2.58. And you get, let's move it down here with a little more room. 273.5058 grams. That's what my calculator tells me. But you know from previous work on significant figures, you've only got 3 significant figures here. So we have to round it off to 274 grams. And so there it is, 274. Now, I went through this first one in nauseating detail because when we reach other problems that need some of these steps, I won't have to go over it again. We'll just do it. All right, number 2. .52 grams of water contains how many molecules of water? Okay. The question, how many molecules of water? That means we have to calculate exactly how many molecules of water in that many grams. That's going to be a big number. I mean, you just know that going in. We start off with 8.52 grams of water. Is there a conversion factor that will convert grams to molecules? The answer is no. We have a conversion factor that will convert to moles. That goes from mass to numbers. And then we can take numbers to other numbers. Okay. So we convert this to moles first. If you calculate 2 hydrogens and 1 oxygen, the molar mass is that. Okay, so we got rid of the grams. Now we got to convert moles to molecules. What's the magic number? 1 mole is equal to 6.022 times 10 to the 23rd things. In this case, molecules. So there's our conversion factor. All right. Moles cancel, we're left with molecules, so we know we put the right values in there. All right, so what should that be? Well, to save time, it's going to be 2.85 times 10 to the 23rd. Molecules. And that is a huge number. That was 2. We're going to start picking up the pace here. 3. How many moles of aluminum oxide? Isn't that nice? They give you the formula. Aluminum oxide are present in 78.8 grams of the compound. 78.8 grams of that compound. How many moles is it? You need your conversion factor to cancel grams and leave you with moles. So when you see grams and moles in a quotient relationship like that, always think molar mass. So what's the molar mass of aluminum oxide? Well, we need 2 aluminums. All right, aluminum is 2698 and 3 oxygens. Okay. So 2698 times 2, and then 48 for the oxygens. 101.96. Right. So does that answer our question? Yeah, how many moles? So we do the math. 78.8. Divide that into it. 0.7729 moles. 3 significant figures. So I got to round it off. There you go. And that's A. There. 4. Which of the following compounds has the greatest percent by mass of oxygen? This is going to take some work. In this case, we want to use Henry Ford's method. Set up an assembly line. You're going to do the same operation for each one of these. First thing you have to do to answer that question is percent by mass. You've got to find out the mass, the percent of oxygen in each one of these by mass. Right? We know how to do that, but you've got to have the formula, the compound formula to do it. So potassium carbonate. What is that? Potassium. There's carbonate. Right? 2 minus, we need 2 of those. That's a type 1 compound. B, nitric acid. We know it starts with H. And nitric, that means there's oxygen there because there's no hydro in the name. Nitric, X come from 8s. So nitrate is the rest of the molecule. C, zinc 2 oxide. This is a type 2 compound. So zinc with a 2+ charge is with oxygen with the 2- charge. That's it. We only need 1 of each. And D is sulfur dioxide. Right? What type of compound is that? It's a type 3. Sulfur and oxygen are both nonmetals. And there's another giveaway here, the dioxide. In a type 1 or a type 2, you don't have to say mono, di, tri, tetra, whatever. So sulfur dioxide. And the last one, diphosphorus pentoxide. Diphosphorus pentoxide. Okay, now what we need is to set up our formula so that we can calculate the percent oxygen in each one. Okay. So they're going to be each one is going to have a divisor, and on the bottom is going to be the total weight of that compound. So, 2 potassiums, 39.10. 39.10 times 2 is potassium. Carbon is 12.01. And 3 oxygens is 48. So that's 138.21. 138.21 is the total mass of 1 mole of the compound. Well, if you have 1 mole of this compound with that mass, then what mass of that compound is oxygen? It's 48 times 100. Okay? So since I've already got it in my calculator, I'm going to have to do that calculation. Let's see. 4 significant figures, 3473. This is oxygen, percent oxygen. Okay. Nitric acid, HNO3. So we have 1 hydrogen at 1.01. We have 1 nitrogen at 14.01. Yes. And we have 3 oxygens again, 48. So that's 6302, 63.02 grams. And we have 3 oxygens again, so we're 48 grams times 100. And that comes out to 76.17. Okay. Zinc oxide. Zinc is 65.38. And oxygen is 16. So the total is 8138. And oxygen is 1 of those atoms. So I need 16 divided by that value, 19.66. Okay, sulfur. Sulfur is 3207. I'm getting these numbers right off the periodic table. And 2 oxygens, which is 32, 16 times 2. 6407 is total, and the oxygens are 32. So let's divide 32 by that number. And I get 49.95%. And the last one, phosphorus, 30.97. 30.97 times 2 plus 5 oxygens. Right? What's 5 times 16? 80. Let me see. 16 enter 5 times. Yeah, 80. Add those together, 141.94. That's pretty bad. Try that again. And then 5 oxygens was 80 times 100 equals 5636. Okay. So now we can answer the question. Which one has the greatest percent by mass of oxygen? It's this one right here, nitric acid. Okay. That's what you have to do to answer the question. All right, number 5. I'm going to have to scroll this one. All right. Number 5, compound X2Y. That's a hypothetical compound. We don't know what the X is or what the Y is. We're just saying that the ratio of atoms in the molecule is for every 1 Y, you have 2 X's. And it's known to be 60% X by mass. Okay, we know that. What's the percent Y by mass of the compound here? If we have this compound made up of the same 2 elements, but in a different ratio, what we want to know is what's the percent question, percent Y by mass. Okay, so notice I extracted all the information I could from that problem and put it on the board in a way that we can better understand it. Now we can draw some conclusions and logically estimate the percent by mass of Y. Remember what, let's see, I think it was Proust. Proust said that every compound, no matter where it's derived, every compound has a fixed ratio of masses of the elements in the compound. So if you get water from distillation or water from the combustion of hydrogen and oxygen, you can't tell the difference. They're both the same compound and they're both the same ratio of hydrogen to oxygen. In this case, the ratio of this X to that Y is, if it's 60% X, it has to be 40% Y. Okay? Now, we can't do much with that, with percentages. But what if we have 100 grams of the sample? If we have 100 grams, then we have 60 grams of X and 40 grams of Y. Okay? Now, if we have In this case, if we have 60 grams of X and 40 grams of Y, how much is individual X? The individual X is 30 grams per X. So if we have two, well, now that didn't help any. Now on this side, if we have however many grams we need, right, we're going to do the ratio and say we want 60 grams of X would be 2, but 2 Y's would be 80 grams of Y, right? Because this represents only 1 gram, 1 Y. So 2 Y's would be this. Now the total is 140 grams, right? So the ratio percent by mass is Y divided by the total, right? Times 100. So if we do 80 divided by 140, excuse me, and multiply by 100, we get, let's see, 2 significant figures, 57% Y is the composition of that compound right there. Okay? Let's see, that was 5. Let me see if I can get to the next one. A lot of these are repetitious now, so I'm going to skip a few. There's 12. Let's do 12. Or, yeah, we can get A, B, C, D, E. We can get 12 and 13. What's the mass of 5.826 moles? 5.826 moles of calcium hydroxide. Now, haven't we done one of these before? Well, yes and no. What we didn't have before was this parentheses. This problem is designed to check to see if you know what to do with a parentheses that has a subscript. So if we have this many moles of that compound, 8.26 moles, and we want to convert it to mass, right, grams, then we need a conversion factor that will get rid of moles and leave us with grams. We need the molar mass of that compound, right? So calcium is 40.08. Right? Calcium is 40.08 grams. Oxygen, how many oxygens do we have? We have two oxygens. Right? So that's 32 added to that one. Let's see, 40.08. Let me do it again just to be sure. Okay. And then we have 2 hydrogens. Right? So the molar mass is 74.10. And then just to be complete, 5.826 times that value is 431.7066. We have 4 significant figures, so 431.7 grams. There it is right there. All right, let's take a look at 13. Choose the pair of compounds with the same empirical formula. All right. Empirical formula. Is what? It is the simplest whole number ratio of atoms in a formula. So if it's I don't know, H8O4, that's not the simplest whole number ratio. because you can divide through the whole thing by 4. If you do that, then you get H2O. All right. So which one of these have the same empirical formula? Well, in order to do that, let's take that example, the first one. If we say water, then anything else, this is very simple. This is 1, 2. Can't get any simpler than that. Anything else would have to be a multiple of it. It would have to be H4O2 or H6O3, right? So H2O2 is not the same empirical formula. What is the empirical formula of that? HO. C2H2, C2H2, and C6H6. What's the empirical formula of this one? Divide through by 2, CH. Divide through by 6, CH. There's your answer. Right there. We don't even have to go any further. You have to have the same elements in each compound, plus they have to be multiples of each other. So this multiple is 3 times, but when we simplify it, it's only 1 carbon, 1 hydrogen, 1 carbon, 1 hydrogen. That's number 13. Number 15. If we can get that one in before I have to walk over and scroll. 15. What's the molar mass of barium hydroxide? Okay. This is actually simpler than the ones we've been doing. You have to know where barium is, right? You'll find it in the second column, the alkaline earths, and it's a big, big atom. 137.327, 137.3. 33. 137.33, rounded up to 2 places. 2 oxygens and 2 hydrogens. Right? Add them together, and you should get 171.35 grams per mole. All right. 16 and 17. Calculate the number of molecules in 0.000400 grams of gaseous oxygen. Remember when you were memorizing the symbols from the periodic table? There were a few of those that had a blue highlight or blue background. Those were diatomic elements. Gaseous oxygen is not this. Gaseous oxygen is that. This is one of those cases, if you don't know that it's diatomic, you will get the problem wrong. So if we have this many grams, okay, we're going to convert it. We want to know molecules. Right? We know how many of those are there. Well, we can't go straight from grams to molecules. We have to go to moles first. And the molar mass of that oxygen is this. Right, so grams are canceled. Now we can convert moles to molecules. Moles cancel, these are some molecules. Excuse me. And that answer should be 7.53 times 10 to the 18th. Molecules. Okay. How many atoms do we have of oxygen? Twice that many, right? For every one of these, you got 2 atoms. This is molecules. So you would have twice that many atoms of oxygen. All right. 17. 22.6 grams, 22.6 grams of copper represents how many moles? All right. What is the molar mass of copper? Let's see. 63.55. 63.55 grams per mole. Right? So if that's a mole, what's this? It's about a third, right? That's about a third of that value. So I don't even have to do the calculation. This is multiple choice. That's your best answer right there. About a third of a mole. You can do the calculation, sure. Just do it like this. Put gram on the bottom, moles on the top, and 63.55, and then calculate it. 0.356 mole. But if you're in a hurry and you know what you're doing, you can estimate and pick the right answer sometimes. In this case, it was really easy. Let's see, number 19. Calculate the number of moles of chlorine molecules in a sample that contains 7.380 times 10 to the 25th molecules. Okay. So we need to know how many moles of chlorine, Cl2, right? That's one of those diatomics. Our starting position is 7.380 times 10 to the 25th molecules. If it just needs to know how many moles, it's a simple calculation. Molecules, moles. 1 mole is 6.022 times 10 to the 23rd. Okay? So 6 into this is greater than 1 times 23 subtracted from 25 is 10 squared, right? So something greater than 1 times 10 squared. Hold on a second. What did I do? Oh, yeah, okay. That's 10 squared would be 100 something. It's greater than 100, right? But it's not that small, and it's not that big. Look at that size of that thing. And it's not this one, right? Because it's greater than 100. Okay. You can do the calculation, sure, right? Whatever's comfortable. But I can answer that question as C right now without doing the calculation. Well, not doing an accurate calculation. I can estimate and get the right answer in this type of arrangement. All right. 22, I'm going to scroll. All right, number 22. Acetylene gas is 92.3% carbon, 7.7% hydrogen by mass. That's it. That's all there is to it. Its molar mass is 26 grams per mole. What's its molecular formula? Okay. So remember how you determine the molecular formula? You've got to do the empirical formula first. Then you can use this extra bit of information to complete the process and find the molecular formula. So the empirical formula, we start with 92.3% carbon and 7.7% hydrogen. That's it. Add them together, you get 100%. But we can't work with percent, right? Formulas are ratios of atom to atom or mole to mole, numbers. This is mass, right? So in order to convert mass into something we can use, we need to have actual mass values, grams. So that's where we assume that we have a 100-gram sample. Right? 100-gram sample. That means 92.3 grams of carbon and 7.7 grams of hydrogen. Now we can work with it. We can convert these. Let's see, carbon is 12.01 and hydrogen is 1.01. Right? Grams cancel. We're going to have moles left over. All right. So 92.3 divided by 12.01 is 7.69. 7.69. And that's moles. 7.7 and 1.01 divide is 7.62. Okay. Now, normally what we would do is take the smallest one here and divide everything through by it. This is mole ratio. It's just not whole numbers. We have to get whole numbers. But notice that they're so close together. This would be approximately ratio together would be 1:1, right? 1:1. So that means the empirical formula is CH. Now we need to work toward the molecular formula, right? So we need our multiplier, whatever that value is. Well, the empirical weight of CH is 12.01 plus 1.01, 1302. So this one is 13.02 grams per mole of that formula. But the molecule, the molecular formula is 26 point, it just says 26 grams per mole. Right? So if N equals 1, the molar mass of the compound would have to be 13.02, but it's not. So if N is 2, then the molar mass is very close to 26. That means N equals 2, and the molecular formula is C2H2. Right there. All right. Let's see. Yep, I'm going to have to scroll again. What about that? 24. The molar mass of ammonium phosphate. Okay. Here's another one where you've got to know how to write the compound formula. Otherwise, you can't calculate the molar mass. Ammonium. What's ammonium? It's not an element. It's a polyatomic ion. In fact, it's the only polyatomic ion in that list I gave you that is a positive charge. This is ammonium. Phosphate is also a polyatomic ion. So you look it up, PO4, it has a 3- charge. Right? So we treat this like a type 1 compound because that occupies the metal's position and it has a fixed charge. So we just balance the charges. We need 3 of these, right, to balance those 3 minuses. Now we can determine the molar mass. So how many nitrogens do you have? You have 3 with that value for nitrogen. You have 12 hydrogens. Okay? 3 times 4, 3 times 1. And 1 phosphorus. which is 3097. And 4 oxygens. Okay. So let's add them up. 3 times 14.01 is 42.03. Then 12 times 1.01 is 12.12 plus, and then 30.97 for phosphorus. And then 4 times 16. Do that one in your head. 64. 149.12 grams per mole. Okay, the closest one is this one. Right? You know why it's that different? Probably because of this one. Most textbooks will just say 1 gram per mole for hydrogen, but actually it's 1.01. All right, so that's the best answer, 149.09. All right, let's see, that was 24. Let's see, 27. 26.4 grams of nickel represents how many atoms? All right, this is simple. I'm just going to set it up and not do the calculation because we've done this kind before. 26.4 grams. If you want to know how many atoms, actual atoms, you got to convert it to moles first. So nickel is 5869, 58.69. Grams cancel, leave you moles. Now we convert moles to atoms with Avogadro's number. Right. And that should equal 2.71 times 10 to the 23rd atoms. Right? Now it's 27. Yeah, we can still see 31. Okay. 31. What's the mass of 8 atoms of copper in grams? Okay. That looks like a huge challenge, doesn't it? You're given 8 atoms of copper. If you need to know the mass, you got to find out how many moles that is. Convert that to moles, and then you can use molar mass of copper to find out what its mass is. Okay? Well, here's one thing we can do. If you've only got 8 atoms of copper, they're not going to be this mass. They're not going to be that mass. They're not going to be this mass. It's going to be one of these two. Right? So, convert to moles first from atoms. 6.022 times 10 to the 23rd atoms per mole. Now we got rid of atoms and we need to convert moles to grams. Moles on the bottom, grams on the top. And copper is 6538. There we go. Now you do your math and you should come out to 8.44 times 10 to the minus 22 grams. All right. This chapter has a lot, a massive amount, a massive amount of dimensional analysis. Conversion factors. Let's see, we're skipping some, all this repetition. I even threw that one out because it just wasn't a good question and we hadn't got to that topic yet. So how about 43? 7.98 moles of sulfur trioxide. 7.98 moles of sulfur trioxide. We're given that. You have to write the compound, I'm pretty sure. Contains how many oxygen atoms? Okay. If this is so many moles of that compound, the conversion factor simply means if this is the compound, you need to convert moles of compound to moles of oxygen. All right, so you can cancel this one, leaves with moles of oxygen. So for every 1 mole of compound, how many moles of oxygen do you have? So for trioxide, for every one of these, you have 3 oxygens. So 3 times that value, 3 times 8, it's about 24. Oh, it's about 24 moles. Okay, this is moles of oxygen. And then we want to calculate how many, let's move it down here. Then we want to get rid of moles of oxygen and make atoms. So that's when you use Avogadro's number. And if we get our calculations right, we should come out with this atoms of oxygen. Okay. Let's see, 49. I have to scroll that one a little bit. See, yeah, I'll just put it in the middle. 49. 4 molecules of chlorine weighs what? Okay, notice, look at the answers. Some of them are in atomic mass units, and some of them are in grams. So, if we have 4 molecules of chlorine, this is a molecule of chlorine. That's first, you have to know that. It's a diatomic molecule. So, 4 molecules, 4 molecules of that. We don't find out what does it weigh. Well, 4 molecules would be how many atoms? Right? I'm going to do this longhand. Molecules, atoms. So we've got molecules cancel. For every 1 molecule, you have 2 atoms. So we have 8 atoms of chlorine. So how much does each atom weigh? We'll do the AMU first, atomic mass units. Maybe that's one of the answers. So for every atom, you have, for chlorine, you have 35.45. 35.45 atomic mass units per atom. Right? So 8 times 35.45 will give us 284. 284 atomic mass units. Okay, wow, there it is, right there. We didn't even have to go to grams. Right? We found our answer. All right, 53, you have to scroll that one too. Okay, 53. Great. Which represents the greatest mass? Okay, so these are our choices. All the same? We don't know that unless we work every one of them. B, a 1 mole of iron. Mole of iron. 1 mole of aluminum. 1 mole of rubidium and 1 mole of titanium. Okay, you got a mole of each. Which is the greatest mass? Well, they can't all be the same because every element has a different molar mass, right? So this one's out right off the bat. So we just need to look up their molar mass in grams or atomic mass units. It doesn't matter really. They're the same number. If you got 1 mole of each, iron is about 56. I'm going to estimate. Aluminum is 27. Rubidium is about 85. And titanium is about 48. Right? So there's the heavyweight, rubidium. All right, scroll. 61. Let me see. I'll be able to get both of them on there. There we go. 61. A sample of metal weighing 2.59 grams. So we got a metal. A pure metal weighing 2.59 grams is combined with oxygen. So let's give it a symbol, call it M. Is combined with oxygen. The metal oxide weighs 3.01 grams. Oh, I'm making this more difficult than it should. It's combined with oxygen in some proportion. The metal oxide is 3.01. So the total mass is 3.01 grams. And the metal in that sample is 2.59 grams. Okay. So the mass percent of the metal is what? I'm going to work it backwards. Oh, we can do it this way. If that's the mass of the metal, what's the mass of the oxygen? It's 3.01 minus that. So if we say 3.01 minus that, divided by the total times 100, we should get 14% oxygen. Okay, 62. What's the molar mass of nitroglycerin? Okay, this will take some work. H5NO3 taken 3 times. Okay, so all we need to do is say 3 times 12.01 for the carbon, 5 times 1.01 for the hydrogen, 3 times 14.01 for the nitrogen, and 9 times 16 for the oxygen. Add them together. And we should come up with 227 grams per mole. Okay. Now 62, 63. A certain compound has an empirical formula, NH2O. NH2O. That's the empirical formula. Its molar mass is between 55 and 65. So I abbreviate that molecular weight is 55 to 65 grams per mole. Okay, what's its molecular formula? If this is the empirical formula, we need to find the multiplier. But I've been using N, haven't I? Let's use N. So what's the empirical weight of that? Well, that's nitrogen. That's hydrogen. That's oxygen. So we have 3, 0, 8, 12, 3203 grams per mole of that formula. Okay. So if N is 1, then 32 is not between 55 and 65. If N is 2, then it's 64. It is between. So N equals 2. And the formula then is N2H4O2. All right. '64. The molar mass of blood sugar, also known as glucose or dextrose, is what? C6H12O6. So you just need 6 times 12.01 for the carbon, 12 times 1.01 for the hydrogen, and 6 times 16 for the oxygen. And together, that number, if you do it that way, is probably going to be bigger than the one they give you here. So it's going to be in the neighborhood of 180.16. My value is probably a little higher than that because more than likely they used just 1 for this one. All right. Let's see, page down, 67, need to scroll that one. Yeah. 67. Determine the percentage composition by mass of lead in this formula. All right, we know how to do that. What's that name? All right, can you name that compound? All right, well, we know it's lead. And we know it's fluoride. But what's the charge on the lead? This is a type 2 compound. Remember, lead is in that part of the periodic table where it could have multiple charges. And in fact, it does. Well, fluorine's always -1, so that means this one has to be a +2 to balance those 2 minuses. So this would be a lead 2 fluoride. All right, now that doesn't answer the question. What we need for the question is what's the total mass, and then what's the mass of lead? Lead is 207.21 grams per mole, and that goes together with 2 fluorines plus 2 times 19 times 100, and that will give you the percent by mass of lead in this compound, which should be in the neighborhood of 84.5%. All right. 75. Calculate the number of moles of water molecules in 72 grams of water. Okay, I'll set this one up. We're starting with 72 grams of water. How many moles is that? No, number of moles of water molecules. So all we need to do is convert it to moles, right? Use the molar mass there, 18.02. And 18 into 72 is about 4. Yeah. In fact, they're saying it's exactly 4. I just did that in my head. I say, what times 18 will give you 72? Well, 2 times 18 is 36, and 2 times 36 is 72. So 2 times 2 is 4. There's your answer. Right, 77. What's percentage composition by mass of oxygen in this compound? How would we name that? Well, what type of compound is it? Where's the lithium come from? Lithium is an alkaline metal, so it's a +1, it's a fixed charge. So it's a type 1 compound. We would just say lithium, and then the polyatomic ion, sulfate. That's it. Done. Oh, we haven't answered the question yet, though. What's the percentage composition of oxygen? So what we need is 4 times 16 in the numerator. In the denominator, we need 4 times 16. And then we need to add sulfur to it. 1 sulfur, 3207. Right, 1 sulfur. And then 2 lithiums. And lithium is a pretty light molecule, atom. 6.94. 6.94. Okay, then times 100. And that should give you 58.21%. Okay. All right, 78 times scroll. Yep. My marker's getting a little weak. 78. A compound is analyzed and found to be 12.1% carbon, 16.2% oxygen, and 71.7% chlorine. What's the empirical formula? Right? We did one of these for acetylene earlier. So I'll set it up for you. But I might as well go through the whole thing. 12.1% carbon. So there's carbon, 12.1%. Oxygen is 16.2%. And chlorine is 71.7%. Right? So when you're faced with this problem, you assume 100 grams. Why? Because percent is parts per 100. So if we say it's 100 grams, then the value of percent is the mass. So this is 12.1 grams of carbon. This is 16.2 grams of oxygen, 71.7 grams of chlorine. All right, now we can convert grams on the bottom, moles on the top. All right, this is 12.01. This is 16. And this is 35.45. You know what I see? We're going to come out with very close to 1 here. Very close to 1 here. And very close to 2 here. So I would venture COCl2. Right there. Now, if you want to, you can go ahead and do the calculations and find out exact numbers, but then you've got to ratio them and get them down to whole numbers. And I just saw an opportunity to knock this one out. That into that is about 2, about 1, about 1. So we're going to end up with a 1:1:2 ratio anyhow, no matter how you go about it. And that just saves you time on a test. All right. Let's see. 83 just got cut off. Let's go up a little bit. 83. I think I'm going to have to retire that one. Here we go. $83. All right. You have 12.6 grams of an unknown substance A. 12.6 grams of A, right? 35 grams of chlorine gas. 35 grams of chlorine gas, Cl2. Substance A contains 1.5 times as many molecules as chlorine gas. All right. So if this one has 1.5 times, then let's say, well, how many moles is that? Right? We know chlorine gas is 35.45 grams per mole. So if we convert that, if we convert this, that's about 1 mole. Let's do the exact value. Okay. Let's calculate that. 35 divided by 35.45. Oh, excuse me. That's wrong. This is per atom. I'm talking about molecule. So the molar mass of chlorine is 70.90 grams. So divide is 49370, 0.4937 moles of chlorine. So 1.5 times that, see, times 1.5 equals 0.7405 moles. Right? How is one way to determine, there are basically 2 ways to determine an element. If you know the number of protons, if you know the atomic number, that's surefire. But another way is if you know the molar mass of the element, grams per mole, then you can usually find it that way also. That's the choice we have here. We've got this many grams and that many moles. 12.6 grams per 0.7405 moles. So let's say 12.6 and divide into 17. 17.02 grams per mole. So let's look at our element. 17.02 grams per mole. Well, it's kind of in between. Oh, okay. I see the problem. We're given choices here. This is not an element that we're looking for. We're looking for a compound. We know it's not oxygen because oxygen is 32 grams per mole. C, D, E. So A, uranium fluoride. Uranium fluoride. 6 fluorines is more than that. So that can't be. And uranium is a huge, it's let's see, 238 grams per mole. Right? So we can't be that one. How about the next one? Oxygen. Oxygen is 32 grams per mole. Right? So it can't be that one. Ammonia. Ammonia is 14.01 plus 3.03 for the hydrogens. That's about 17.04. There it is right there. Ammonia. That's the answer. We found out the molar mass of the compound, and then we had to calculate the molar masses or estimate the molar masses for our choices. And that's the only choice that works. We could do the other 2, but we found our answer. And if you're in a hurry taking an exam, Once you find your answer, you can stop. Why? Because there are no more oddballs in here, like one of the above, two of the above, none of the above, all of the above. If there are none of those in there, you just work your way down until you find the answer and stop. As long as you're doing the problem correctly, as long as you're working it correctly, then you can do that. You can stop. If you're unsure of yourself, then you got to go through all of them and then flip a coin. I don't want to do the test that way. I want to know how to work the problem and get the right answer under any set of circumstances. So 88, what's that? Another percent composition of magnesium in this compound. Right? ASO4. And that's 2. And this is 3. Okay? This is a dead giveaway. When you've got something inside of parentheses that has oxygen with it, that's a polyatomic ion. So you can look it up. That's the arsenate ion. And in fact, it has a 3- charge. And this one has a +2 charge. We know magnesium has a +2 charge because it's an alkaline earth. Fixed charge. So we would call that magnesium arsenate. I'm pretty sure. Let me check. I don't want to tell you wrong. Let's see. Yeah, that's arsenate. Arsenate. I didn't want to get it confused with this one. That's arsenite. Okay, arsenate. Okay, now we want to calculate the percent by mass of magnesium. So what we need in the numerator is the mass of 3 times 3 of these magnesiums, which is 2431. Right? Then we need the total in the denominator. So we need that one again because it's part of the total. Plus, how many arsenics? 2 arsenics. So we go find arsenic. 7492. 2 times 74.92 for the arsenic, and then 8 oxygens. That's 8 times 16. There we go. And all that's times 100. All right, if we do our math correctly, we should end up with 20.8% magnesium. All right. 91, I can see the whole thing down there, so we'll just do this one, 91, like that. A compound is composed of element X and hydrogen. That's X and hydrogen. We don't know what their ratios are yet. Analysis shows the compound is to be 80% X by mass. So this is 80% by mass. That means hydrogen is 20%, correct? There you go. With 3 times as many hydrogen atoms as X. So if this has 3 times as many atoms, we know that that's 3. Which element is element X? Well, if we know that the mass is 20% of hydrogen, then what if we have 100 grams of the sample? Then we have 20 grams of hydrogen, right? And we have 80 grams of X. All right. So how many moles of hydrogen do you have? 1.01 grams per mole equals, yeah, I probably ought to just estimate 19.8 moles of hydrogen. So it's that many moles of hydrogen, and this is equal to 3 times the moles of X. So moles of X has to be 3 divided into that, or 6.6 moles of X. Now we got moles of X and mass of X. So we got 80 divided by 6.6. Back 80, 6.6. There we go. 12.1 grams per mole. So which element, X, is close to that? Right? Look on your periodic table, and you'll find that the closest one to that is carbon. Okay? There it is right there. Now, the fact of the matter is, I don't know of any compound that has this formula. But maybe it exists, but I've never seen it. So this is purely hypothetical. That was 91. Let's see, 94. I think, yeah, we got everything on there. 94. You have 2 beakers on your table. Beaker one has what? 32.07 grams of sulfur. Sulfur, 32.07 grams. Okay. Beaker 2 has 74.92 grams of arsenic. Okay. Which beaker contains the greater number of atoms? Well, let's see. I should have done it. Let's be consistent. Arsenic. There we go. Well, if we want to compare the number of atoms, we need to convert these to moles. Right? If you convert to moles, then you've got numbers, and you can compare, you can ratio them. You don't have to go all the way to atoms. If you got moles, you can find out the ratio. So sulfur is 3207 grams per mole. So that's equals 1 mole. Arsenic is 74.92 grams per mole. So that's 1 mole. Right? So they both have a mole. Which beaker contains the greatest number of atoms? Beaker 2? No. Beakers 1 and 2 contain the same number of atoms because there is 1 mole in each. There's your answer right there. It helps to draw a picture, because that's a lot of words up there that can spin your head around. If you draw a picture, then you can extract the information and make sense of it. All right, scroll time. '97. Convert 4.13 moles into molecules of PCl5. This seems repetitious. It's not like me to do that, but it is what it is. If you got that many moles of PCl5, how many molecules do you have? This is one of those cases where it doesn't matter. If you've got 4.13 moles of the molecule, then you can calculate the number of molecules and you don't have to know that it's PCl5. Because we're converting moles to molecules with the same conversion factor. All right. So 4 times that is about 2.4 times 10 to the 24th. Yeah, right here. 2.49 to be exact. All right. That was pretty easy. All right, let me scroll just a hair. I think there's one missing on number 100. Yeah. Okay, 99. 5.392 grams of hydrogen gas contains what? 5.392 grams of hydrogen gas. Diatomic. Well, let's see. What are our choices? Atoms of hydrogen, molecules of hydrogen, atoms of hydrogen, or atoms of oxygen. If it's a hydrogen gas, there's no oxygen there. Right? So we can throw E out. E's gone. That many grams of hydrogen is going to be more than 5 atoms. Right? So it's one of these. It's either this many or this many molecules or atoms of hydrogen, or it could be this many moles of hydrogen molecules. Right? So let's convert it to moles first, because unless we convert to moles, we can't answer any of these. Right? We got to go through moles, and then maybe we can go to molecules if it needs to be, or atoms if it needs to be. So the first thing we have to do is find out how many moles of that there are. 1.01 grams per mole of hydrogen gas. So divide 5.392 under 1.01, and that's 5.34. 34 moles of hydrogen gas. It's not quite, let's see, 339. Right. If we bring it out some more, it would be 39 moles of hydrogen gas. I'm tempted to pick this answer, but just to be sure, let's convert that to molecules also. 5.339 moles of hydrogen is how many molecules, right? So we have moles on the bottom, molecules on the top. 10 to the 23rd molecules. And so 6.022 exponent 23 times. This is 3.215 times 10 to the 24th molecules of hydrogen. Okay, that rounds off better to B. Yeah. Yeah. It can't be hydrogen atoms because hydrogen atoms would be twice this. So actually, it's a battle between this one and this one. The answer here is closer to this one. This one's not as close to C as this one is to B. So the best answer, that's wrong. Oh, you know what I did? I made a rookie mistake. A horrible rookie mistake. That's a diatomic molecule. Its mass is 2.02. .6695 moles. Now times Avogadro's number. So that's 1.6076 times 10 to the 24th molecules. That's not up there. How about atoms? Well, it's times 2. So it'd be 3.215 times 10 to the 24th atoms. That's the closest one right there. All because I made that mistake right there. 100. Consider equal mole samples of dinitrogen monoxide, aluminum nitrate, potassium cyanide. Rank these from least to greatest number of nitrogen atoms in each sample. Okay. In order to do that, if we have equal mole samples, let's just say 1 mole of each. If we have 1 mole of each, what we need is, in order to count the number of nitrogen atoms in each sample, we've got to have their formulas. Right? So we need dinitrogen monoxide, that one, which is laughing gas, nitrous oxide. Aluminum nitrate, aluminum NO3, that's a minus charge, this is a +3, so we need 3 of those. And potassium cyanide, potassium cyanide, that's a minus, that's a plus, they're good. All right, so if you've got a mole of this one, a mole of each one, 1 mole, 1 mole, 1 mole. How many moles of nitrogen do you have? We have 2 moles here of nitrogen. Here we have 3 times, that is 3 moles of nitrogen. And this one has 1 mole of nitrogen. Right. So in order from least to greatest, it's potassium cyanide, then dinitrogen monoxide, and then aluminum nitrate. So that would be potassium cyanide, yes. Dinitrogen monoxide, aluminum nitrate. E. E is the answer. Okay. You got to be able to write the formulas, or you will never answer this question correctly. .100, 101. We're doing on time. Okay, we got a half hour. Calculate the mass of 3.53 times 10 to the 26 atoms of silver. 3.53 times 10 to the 26 atoms of silver. We want to know the mass. Atoms of silver. Well, we don't have a conversion factor that will go straight from atoms to mass. We have to find out how many moles there are first. 6.022 times 10 to the 23rd atoms in 1 mole. Right? Takes care of that. Now that we have a mole, we just need the molar mass of silver, which is 107.87. Right? There we go. So that gets rid of moles. Now we have mass. And that's what the question was. Mass. So if we do that calculation, we should end up with 6.32 times 10 to the 4th grams. Does that seem reasonable? Well, that's about 0.5 times 10 to the 23rd, 10 to the 3rd, or 5 times 10 squared, or about 500. And then 500 times 100 would be 50,000. So that's pretty close. That's 63,200. So we could probably do that one in our heads and come up with this one, because you look at this one first, right here, and then you look at this part. All right, so the answer is C. In 106. It'll be getting close to the end here. The mass in grams of 3.52 moles. 3.52 moles of nitrogen gas. All right. It's like we're getting simpler as we go. So how many grams per mole of nitrogen gas? Well, nitrogen is 14.01 for one, but we got two. 28.02. There we go. So 3 times 28 is 4, and 6 is 8, and then a half of that is 14. So that'll be in the neighborhood of 98. Right here. 98.6. I just estimated. You can calculate it out if you want, just to be sure. That's fine. I like to estimate every now and then just to keep my mind active. 110. Scroll time. Let's see. Yeah, there's that. 110. Okay. Calculate the molecular formula of a compound with an empirical formula, CH2O. CH2O, right? That's the empirical formula, so we need the multiplier. And a molar mass of 180 grams per mole. So what's the empirical mass? Well, 12.01, 2.02 for the hydrogens, and 16 for the oxygens. All right, so that's 3, 0, 8, 10, 3. 30.03. How many times will 30 go into 180? Right. 180 divided by 30. It's about 6 times, right? So N equals 6, C6, H12O6. Probably glucose. We saw that one in a previous problem. And 113. A 60.2 milliliter sample of mercury. Okay, we got volume of mercury equals 60.2 milliliters. Density of mercury is 13.6 grams per mil. Contains how many atoms of mercury? Well, we've got volume, we don't have mass. We can't convert to number of atoms or moles first, unless we know what the mass is. So remember your definition for density. Mass per unit volume. So the volume is in the same units of measure, that's good. And we need to solve for mass. So mass equals density times volume. 13.6 grams per milliliter times 60.2 milliliters. Right? Milliliters cancel. And the mass, let's put the mass over here. The mass equals 13.6 times 60.2 is 818.72 grams. Since all of our activities now are multiply, divide, I'm going to keep all of my decimal points until the end because I don't want rounding errors. So I'm not going to round this right now. It would round up if I kept only 3 significant figures. I'm going to keep these and convert that to moles of mercury. So what's the molar mass of mercury? It's 200.59. 200.59. Right, that gives us moles. How many atoms? Right. So we're going to convert, also going to convert moles to atoms with Avogadro's number. Right? And if we do our math correctly, we should end up with 2.46 times 10 to the 24th atoms of mercury. Okay, that's 113. 116. Let's see. I'm just checking to see if I got any more beyond that. That looks like it's the last one that I have highlighted. Yep. Okay, so we can take our time on this one because we got 20 more minutes to go. So let's do that. $116. Let's see. Vinegar contains carbon, hydrogen, and oxygen with percent masses of 40 for carbon, 6.7 for hydrogen, and the rest is oxygen. If the molar mass of vinegar is 60 grams per mole, what's its molecular formula? All right. So we're given 40% carbon. So I'm going to skip a step. I'm going to go ahead and change it to grams. 100 gram sample means that many grams of carbon and this many grams of hydrogen. So how many grams of oxygen are there? Well, what's the difference? Right. 6.7 plus 40 and subtract that from 100. 53.3. Okay, now we have all of our masses and we can convert the moles. Use Henry Ford. Grams on the bottom, cancel these grams, moles on the top, because our compounds are always written by ratio of numbers of atoms or moles of atoms in the formula. So oxygen is 16, hydrogen is 1.01, carbon is 12.01. There we go. Just do a little quick calculation here. 16 divided. This one is 3.33. And this one is 6.7, 1.01 is 6.63. And then the last one, 40 divided by 12.01 is 3.33. Right? Normally what we would do is take the smallest one, which is both of these. This would be 1, and this would be 2. Right? So you divide them through by 333. These obviously would be 1. And this one is very close to 1. Right? It'd be 6.66. It's approximately 2. Right? So there's our empirical ratio. Carbon, hydrogen, oxygen. Okay, what's the molar mass of that thing? Well, let's add them together. 12.01 for carbon, 2 times hydrogen, 2.02, and 1 oxygen. So that's 30.03 grams per mole. And we were given 60 grams per mole as the molar mass, the true molar mass. So divide this one into that one, and that's approximately 2. So not this N equals 2, we have C2H4O2. That's the molecular formula for vinegar. Actually, that's not the molecular formula for vinegar. Vinegar is acetic acid solution, 5%. So that's really a misnomer. It should be acetic acid. This is the acetic acid molecule, and most of the time, though, we write it like an acid. So we need one hydrogen out here. That's the acidic hydrogen, and the rest of them are locked in place. So this is more commonly the way you will see acetic acid, like that. Take one of these hydrogens, put it out there. All right, I think that's it. It's the last one for this review. And the exam on chapter 8, number 3, is on Thursday the 23rd. I'm pretty sure that's it. Yeah. And you will have all of this information at the back as useful information in the folder where you find exam 3. So like I say before, be sure and print that out before you go into lockdown browser so you can have it available. And there should be, there's some empirical formulas, and there's your periodic table. All right, that's it. We are done.